Okay, I'm a ninth grader from Texas, and my name's Ayush. And today I'm going to be solving ARML 2025 Problem 6, which was this May. So, compute the least positive multiple of 7 expressed as a base 10 number, such that it's exactly 7 ones in binary. So, let's first define what it means if a number n has 7 ones in binary. And this is our keyword, the word binary, which is equal to base 2. So the number has to be in the form 2a1 plus 2a2 plus ... all the way till 2a to the 7, because there's 7 digits in the number, where the numbers are in an inequality of this way, meaning that A7 is the largest number possible. So essentially what we do is that we first, let's just do our first case. That A1 is equal to 6. So essentially, if we check if A1 is equal to 6, the numbers would be 2 to the power of 6 plus 2 to the power of 5, all the way till 2 to the power of 0, which is equal to 64 plus 32, all the way till 1, which is just 2 to the 7 minus 1, which is equal to 127. And clearly, this does not work, as it's no multiple of 7. Now, let's just keep on going up until we can find a value that works. Case 2 is A1 is equal to 7. So, essentially what this gets is n is equal to 2 to the 7 plus 2 to the 6, all the way until 2 to the 0, minus 2 to the b, which is equal to 2 to the 8 minus 1, which is 256, minus 2 to the b, which is where b could be anything from 0 to 6. So now what we do is that we can let this equation be in mod 7. So here we can see that we get the equation as n is equal to 3, because the remainder when this is divided by 7 is congruent to 3. So n is equal to 3 minus 2 to the b mod 7. And because of that, we can see that n is not a multiple of 7 on this case. So now, on to case 3, where we do case 3, where A1 is equal to 8. We get our answer as A1, 2 to the 8 plus 2 to the 7, all the way until 2 to the 0, minus 2 to the b, minus 2 to the c, because we've added 2 extra digits than what should be already previously there. So we have to compute this in mod 7. So what we get is this whole value as 511, because it's 2 to the 9 minus 1, 511, minus 2 to the b minus 2 to the c, which is congruent to 511 is divisible by 7. This is mod 7 congruent to 0. So now we have to do this in terms of negative 2b minus 2 to the power of c. And essentially here, since this is always a multiple of 2, or also known as even, this cannot be mod 7. So now let's go on to our next case, which is case 4. Now if we check, A1 is equal to 9. So now to account for all the digits which we previously added, we do this plus 2 to the 1 plus 2 to the 0. Now we have to subtract digits as we've been doing earlier. Minus 2 to the b, minus 2 to the c, minus 2 to the d, which is equal to 1023 minus 2 to the b minus 2 to the c minus 2 to the d. And as we compute this equation in mod 7, which is divisible by 7, we know that our answer is 1 minus 2 to the b minus 2 to the c minus 2 to the d, where that this requires that this in mod 7 is equal to 2 to the c is equal to 2, and 2 to the d is equal to 4. So now, given this, let's just plug in the values. Well, these values are just as placeholders. But to find n, we have to make 2 to the b plus 2 to the c plus 2 to the d greatest possible. So, to do that, what we have to do is we have to find a configuration where this is congruent in mod 7. And to make k, the equation would work if 2 to the power of k is congruent to 2 mod 7. And we can know that works because k could equal to 1. Then we can cycle up to, 4 and 7. And another solution is 2 to the k is congruent to 4 mod 7, where k is equal to 2, 5, and 7. And if we trial and test for a little bit, using these values that work, we can find that 2 to the 8 plus 2 to the 7 plus 2 to the 4, and then 1023 minus this is indeed congruent to 623. And that indeed is a multiple of